Hello, my name is Luan Guedes Costa, and today I'm going to present to you a work entitled Energy Harvesting from Chaotic Vibrations. This work was done by me in partnership with Eduardo Reis and Professor Marcelo Sávio. The presentation contents, first I'm going to do an introduction about the principles behind the piezoelectric energy harvesting, its applications and motivations. Then I'm going to talk about the physical modeling of those systems, especially the bistable systems. Then I'm going to show you some numerical simulations, an overview of the system dynamics, a discussion about chaotic versus periodic attractors, and a correlation among quantities of interest. Then I'm going to show you the conclusions and possible future works in this field. So the principles of piezoelectric energy harvesting are very simple. Through the direct piezoelectric effect, you can harvest wasted mechanical energy and transform it into useful electrical energy. And of course, it has a vast gamma of applications, as in civil infrastructure, or in biomedical applications, or harvest energy from impacts from rain to power electronic devices. For example, you can use the energy from human motion to power small electronic devices. And of course, from offshore applications, as in those operations, you have a lot of wasted vibration energy. So there's basically two types of energy harvesters. There are the linear systems that are better suitable for specific applications where there's no variation of the frequency operation. And there are the nonlinear systems that are better suitable for general situations where you have great variations in the ambient vibrations. This is the focus of our work, the nonlinear system, specifically the bistable systems with magnetic iterations that basically has two stable equilibrium points and can present chaotic responses. Let's talk about the physical modeling of those bistable systems. Usually in the literature, those bistable systems are represented by those equations of motion in the screen. So the blue term is the damping term, the red term is the nonlinear restitution term that makes the system bistable. The orange term is the coupling between the two equations, the mechanical and the electrical one. The purple term is the forcing term, basically that simulates the vibration environment. And the green term is the electrical resistance term of the system. So to evaluate the instantaneous power of the system, basically the input power is a mechanical power, as you can see, and the output power is an electrical power. So the input power comes from the vibration, and the output power is the energy converted by the piezoelectric element in the system. So to evaluate it in the domain of time, in the full time in which the system is collecting energy, we use the root mean square measurement for the input power and the output power. And with those measurements, we can calculate the efficiency of the system. So now let's do an overview of the system dynamics before we enter deeply in the chaotic characteristics of those systems. So bistable systems exhibit two stable equilibrium points and one unstable equilibrium position at the center. It leads to three patterns of motion. Basically, the first one is the intra-well motion, as you can see here in black, that the system always oscillates around one stable equilibrium position. You have the second one, that's the full interval motion. Basically, it's when the system always oscillates around the two equilibrium positions. And you have the third one that basically is the most complex one. It is a mix of the first one with the second one. At times, the system oscillates around one stable equilibrium position. At times, the system oscillates around the two equilibrium positions. So these kinds of motion are important because it greatly influences the performance of those systems. So in a previous work of ours, we had the necessity of creating a variable that quantifies these kinds of motion. So basically, we uh, started to compare the quantity of jumps the system does, basically when the system jumps from one stable equilibrium position to another, and compare it to the maximum possible jumps the system can do in an interval of time. And basically, uh, for those cases shown here, the interval motion have the intensity of 0. A full interval motion here have an intensity of 100%, and though this chaotic blue here motion has the partial interval motion, basically that is a number between 0 and 100%. So knowing that, let's consider the following parameters. In the following analysis, we will deal with 2 dissipation parameters and 3 forcing amplitude parameters, and the domain of external forcing frequency from 0.01 to 2. The initial conditions of all the simulations are based on the stable equilibrium position of the system. The following methods also have been applied to the system of equations: the fourth order Runge-Kutta integrator, the Poincare maps, and Lyapunov exponents to map and identify chaotic responses to ensure that we are analyzing chaotic motion. So from that, uh, these parameters are now in focus to show you that sometimes in the literature you can find that always full interval motions are better than chaotic motion for energy harvesting purposes. So as you can see here, it's not always the case. As you can see here, chaotic motions sometimes are better than periodic motions, and sometimes periodic motions are better than chaotic motions. So this is why it's important to study the chaotic responses of those systems. Let's now talk about the influence of damping in those systems. So changing damping, increasing damping just increases the efficiency of the system in those initial excitation frequencies here, but in general, increasing the excitation frequency diminishes the efficiency of the system. Also, increasing damping decreases the value for the largest Lyapunov exponent in all excitation frequencies. Now let's analyze the correlation between the largest Lyapunov exponents and the performance outputs of the system as output power and efficiency. Looking at these 2 graphs here, there's a clear nonlinear relationship between the largest Lyapunov exponents and the output power and the efficiency. But something strange happens when we increase the damping, and these correlations seems to be less concise than before. We don't know yet why this is happening, but we are going to address this in future works. So the conclusions: our principal objective was to map and identify chaotic attractors for a different set of parameters and point the benefits of chaotic motions in bistable energy harvesting systems. The general analysis shows the need to distinguish different patterns of interval motion, as it greatly influences the output power of the system. The general complex behavior led to choose only cases where the intensity was 100%, proceed with the analysis, and the correlation analysis shows a clear relationship between the electrical output parameters and the lambda 1, that is the Lyapunov largest Lyapunov exponent. Changes in damping changes this correlation pattern, and the distortion of patterns indicates a possible influence of other variables in these correlations. So future work, we need to do a deeper investigation considering other variables in the correlation between lambda 1 and ultimate power. And we need to do the analysis considering other values of the intensity of interval motion. And of course, we need to do experimental verification. So thank you very much. This was my presentation. If you want, you can access the full text here in this QR code. Thank you very much.